Okay, Vangankar madam, you can start.
A very good evening, respected principal and today's invited speaker, Dr. Anish Gangan, Administrative Officer Mr. Shantesh Ravane, faculty members and their students. I'm Sandhya Vaingankar, Librarian of Sspm College of Engineering and Secretary of Ndli, welcoming all of you. Today, the Central Library Department of our college, in association with the National Retail Library of India and the Indian Institute of Technology Kharagpur, is going to present a webinar on nanotechnology and nanomaterials. The objective of this webinar is to develop fundamental knowledge of nanotechnology and nanomaterials and related fields. Let me introduce today's speaker. Dr. Anish Segangal is mechanical engineering graduate from University of Pune and has done masters and PhD in engineering since science and engineering in 1997 and 2013 respectively from the Indian Institute of Technology, Bombay. Presently, he is working with Sspm College of Engineering, Kalpandi as a principal. He has a patent to his credit and authored several papers in international journals and conferences. Dr. Anish Gangal has delivered several lectures on variety of topics. He has worked in industry as an energy management consultant, worked on government-funded research project, and have been teaching for over 15 years and has a total experience of more than 20 years. Now, I would like to request our speaker to share his valuable thoughts with our participants. Sir, please take a charge of session. Thank you.
Thank you, ma'am. Hope I'm audible. Adnan sir, will you please let me know I'm audible?
Yes, sir, you are audible.
The slides are clearly seen.
Yes, sir.
Okay, thank you. As the first, the title slide says, the topic of today's discussion is synthesis, characterization, and application of nanomaterials. I'll start with some basic things. See, this is a field of research, so I will just speak something, one slide on what is research, and then we'll move to next slides. So, the overall layout of my today's presentation is like this. I'll talk one slide on what is research, followed by what is nanotechnology. We'll discuss about the history of nanotechnology, where it came from, and then what is the purpose of nanoscale, why it is and what it is actually. And then I'll talk about the nanomaterials, wherein I work a lot during my PhD program. And then we'll talk about the synthesis, how the nanomaterials can be synthesized, made. And then we'll move to the, how do I know that whether the material is nano or a bulk material? I will have to characterize it, trying to understand the various properties of nanomaterials and how it's done typically today in the scientific world. And I'll end up with some applications of nanomaterials, nanotechnology in the recent fields. So moving to the first slide, as I told you, what is research? It is a very big world today in the academic field. Everyone wants to do some research. Everybody wants to publish the papers. Everybody wants to file a patent. And what exactly is the research? What it is? So, in the most common parlance, it refers to a search for knowledge. In simple sentence, it is given that research is a search for knowledge. There are various definitions. If you Google it, you will find hundreds of definitions of research. I have compiled a few for you. One can also define research as a scientific and systematic search for pertinent information on a specific topic. So, specific to some topic, when you find out information systematically, we call it research. In fact, it is an art of scientific investigation. The Advanced Learner's Dictionary of Current English says that the meaning of research is careful investigation or inquiry, especially through search for new facts in any branch of knowledge. Regular and more different research of systematized efforts to gain new knowledge. And the last one, but the most appealing one to me, it is research the movement from the known to the unknown. See, we are knowing about something and we move to something unknown. That is research. That's what I personally feel. Moving to the next topic, next slide. What is nanotechnology? It is a very buzzword today. Nanotechnology. Lot of if you have seen some good English movies, you might have seen this. Particularly this word was nanobots that was there in I think iRobot it was there. The Bruce Willis movie, Hollywood movie. The word nanotechnology came into existence that they used some nanites to kill that robot. And there was the same similar thing was there in a movie called as G.I. Joe. Don't remember which part. I think first part of it. The nano robots they completely destroy the Paris that Eiffel Tower. For showing that movie. So that is what is something like nanotechnology. That is a destructive use of nanotechnology. There are a lot of constructive and useful applications also. What is nanotechnology? In simple terms, it is said that the design, characterization, and applications of the structures, devices, and systems by controlled manipulation of size and shape of the materials at the nanometer scale. What do you mean by nanometer scale? In general, we can say it is an atomic scale or a molecular scale or a macromolecular scale. That is nano scale. Then to produce the materials, when I say nanomaterials or nanotechnology, the other idea of that is to produce the materials with at least one novel or superior property than a bulk material. Then we say we are working in the field of nanotechnology. Otherwise, it's okay. Like there it is also some material, nothing more than. Then moving to the next topic, next point, that is let me give you an idea that what is nano, what is the history of nanotechnology, where it started. Recently started actually. It started buzzing recently. It's always there forever. You can see that 2000 years ago, the nanocrystals were used by Greeks and Romans to dye their hair. At those times, the hair dye were used by Romans and Greeks. They used nanocrystals. Then, in the Middle Ages, around 1000 years ago, the golden nanoparticles were used to coloring the glasses, the stained glasses, glass windows. In the real sense, for us, for the relevant, most relevant for us is that when the the great scientist Richard Feynman, he is known as the most innovative physicist, Nobel Award winner Richard Feynman, he said in 1959 that there is plenty of room at the bottom. So people talk about large scales, mega and giga, but then nobody talk about the lower side. So he's saying that there is a lot of space at the bottom means there's a lot of space to do research in the smaller scale. That's what he suggests. From there, the word nanotechnology, rather, the concept of nano came into picture. Then the word in 1974, first the word nanotechnology was used by Taniguchi. He uses this term for the first time. In 1981, IBM developed the first scanning tunneling microscope. Sspm is widely known. Scanning tunneling microscope. To find out to identify what is structure or characterization of the materials at this scale. Then in 1985, the scientists at Rice University discovered a structure of carbon C60 that they call as buckyball, because if you saw the first slide, you saw a rolling ball kind of a structure. That is a C60 structure. The carbon structure is also known as fullerene. It was found when scientists were observing the ashes of the boiler exhaust. The soup they were studying. The Engines of Creation, the first book on nanotechnology by Eric Drexler, that was in 1986. And it went going on in 89. IBM made a logo with the individual atoms. They printed. You can see this IBM logo with, and what you see is the dots, the atoms. In 1991, the carbon nanotechnology was discovered. Carbon nanotubes were discovered. Then further in 1999, the nanomedicine, a book was written. In 2000, the National Nanotechnology Initiative was launched. So this is aging from, so more than 2000 years history it has. And then this is just a history, I would say. But today a lot of work is going on the nanotechnology, or particularly nanomaterials. Nanotechnology is a very complicated thing, because it talks about working with the nanomaterials or fabricating structures or making use of nanostructures. It is not that easy, because and why nanoscale? You can see that a nanometer is 1,000 millionth of a meter. People are interested in this scale because at this scale, the physical and the chemical properties of materials differ significantly from those at a large scale. Large scale or a bulk material, bulk material and nanomaterial. Now this figure will indicate what is nanoscale. The size of the Earth, approximately 1.27 to 10 to the power 7 meters. Now this is the size of Earth. When you compare the football, soccer ball with the Earth, this is 10 million times smaller than the Earth. And then soccer ball and fullerene carbon C60 structure is 1 billion times smaller than the. This is comparable. So this is compared to the Earth. This goes into nano. Compared to the soccer ball, the fullerene C60 structure goes again nano. So this is a nano structure. This is nanomaterial. 0.7 nanometers. On nanoscale and the size effects, you can see the effect of these different effects are there. The nanoscale or the nanosize effect will help realization of the miniaturized devices and systems, while providing more functionality. This is important. It has to provide more functionality. Then attainment of high surface area to automation. When you reduce the scale, it automatically increases surface area. You can try it with a cartoon. Take a tomato, cut it in two halves, and measure the surface area. You can do that. You will find when you cut it in two pieces, surface area increases. I won't say double, but it increases. You get further more parts, it will further go on increasing. What happens is surface area increases. Now, why a high surface area is required, or what is the significance of the high surface area? See, when I have higher surface area, what happens is surface area to volume ratio, that is important. See, the same volume I am working with a small higher surface area. Surface area increases, the chemical properties on the surface they change. Chemical reaction potential increases. The nano size effect will also cause the manifestation of the novel phenomena and properties, including the changes in the melting point and the reactivity, as I told you just. Then the electrical properties like electrical conductivity, thermal conductivity, that will change. The mechanical properties like strength will change. And the optical properties like light emission, transmission, distribution, a lot of absorption, transmission, and reflection. All the three optical properties will change with this change in the scale, change in the size. So this will help you understand it further what is nanoscale. 1 millimeter is the typical size of a grain of a sand. Sand grain is approximately 1 millimeter. You reduce it, approximately 150 micrometer is the diameter of a hair, human hair. Diameter is 150 micrometer. And 10 micrometer is the size of a red blood cell, RBC, that we call. We have the most important constituent, one of the major constituent in our blood. Further you go lower, the transistor is around 35 nanometers. A protein molecule is 10 nanometers. Now the 5 to 10 nanometers is your carbon nanotube, CNT, that is widely known as CNT, carbon nanotube. When you further go down, you will get 1 nanometer is your DNA. And approximately 0.1 nanometer is the atom. Typical atom which I got has a 0.1 nanometer. So this is what changes. See, like you can compare the scale, 1 millimeter to 1 nanometer. So what is nanomaterial? Let us move to the important parts of the presentation today. So it is defined as any material that has unique or novel properties due to the nanoscale, nanometer scale. Nanometer scale structuring, I would say. When I say nanometer structuring, see, anything is nanometer. I can define everything. It is just scaling factor, then I can say anything is nanometer. So less than 100 nanometers said as nanometer. When it is 100 nanometer and less than that, then we say the material is a nanomaterial. Above 100 nanometers, we don't call it a nanometer scale. The materials which are above the 100 nanometers, they are not termed as nanometer scale. Then these are formed by incorporation of or structuring of nanoparticles. A nanoparticle is fine particles which are of nanometer scale. Then they are subdivided into nanocrystals, nanopowders, nanotubes, and so on. A sequence of nanoscale of C60 atoms arranged in a long thin cylindrical nano tube. What are the processes, or how to synthesize the nanomaterials? How to make them actually? Is it easy or it is difficult, or it is common? It is not common as such, but then it is not difficult also. There are different methods. One is a top-down approach and the other is a bottom-up approach. When I say top-down approach, it is like you take a bulk material, you go on reducing the size, and you can make a nanomaterial. The various methods are optical or X-ray lithography, electron beam and ion beam lithography. One of the most common techniques is lithography. In some other presentation, we will discuss these techniques in details because there are two technical things. Atomic force, microscopic lithography, material removal and deposition. So in mechanically, you can just have you seen a mixer grinder at your home? Everybody might have used it. What you do is that you grind it to find particles. You take wheat to a mill and you grind it, flour mill. Find flour of your wheat. The wheat you can measure in millimeters. Flour that is the particle size of your flour is in nanometers. That is nanotechnology. You convert the bulk material into nanomaterial. As simple as that. We have been doing it for thousands of years. That's what I told you. The buzzing started in 1959 when Richard Feynman talked about it. Earlier people were using it, but not necessarily that everything that has been used should be talked about. No? That's what was happening. They were using it for years. And our grandmothers knew that the properties do change when we use the material at a fine scale. And because it is like, see, if you eat, can you eat whole wheat? You cannot eat whole wheat, but you can eat the atta. Wheat flour we can eat, we regularly eat. You cannot make rotis from the whole wheat. Even your body won't be able to digest the whole wheat easily. Because the particle size is more than in your stomach, what happens is a biochemical reaction. And the reactivity is less. When the size, particle size is more and the surface area is less. You eat wheat flour, it digests easily. It gets digested very easily. So that is the basic. I'll just try to explain it to you so that you will understand it better. Then nowadays we talk about 3D printing. Similar things can be done with the nanotechnology also, top-down approach. This is the bottom-up approach. You start making layers of in the fine particles. You like a thin, like the IBM logo you have seen in the last slide. Atoms are placed. Individual atoms are placed. If you go on picking the atoms, then you can achieve the nanomaterial. Layer by layer assembly, self-assembly, molecular self-assembly, direct assembly or coating and growth, polar aggregation. So these are the bottom of approaches. Typically, in the bottom of approaches, we use physical vapor deposition or chemical vapor deposition, PVD and CVD, most commonly known techniques. These are some of the processes that are used for synthesis of nanomaterials. The synthesis of nanomaterials is not a very big thing today. Actually, you do it every day in the flour mill. The flour mill wale ko malum hai how you do it. You mix it every day in it. It doesn't know that this is nanomaterial. That's the only thing. थोड़ा सा thick हो जाता है तो the customer will start firing him. So he knows how fine it should be, depending upon the application. These are some carbon nanotubes. You can see what is the sheet is laid down and then it is rolled to make a nanotube. Is it made like this? No, it is not made like this. It is made typically. When I did it in IIT, I use a technique called as chemical vapor deposition for this. Now, this is a single wall carbon nano, SWCMT, single wall. You can see there is a single wall. So the multi wall or this is a double wall. There are only two walls. This is multi wall CMT. There are multiple tubes. There are multiple walls in this. Now, you consider, just let us see the little bit of comparison. Carbon nanotubes have high electrical conductivity as compared to the simple carbon. They are very elastic, 18% elongation to failure. Then they have very high tensile strength. These are highly flexible, can be bent considerably without damage. So their elasticity is very high, so they can be bent. The bending strength is more. They have very high thermal conductivity and very low thermal expansion. Thermal expansion coefficient is very less. That means receiving heat, it doesn't expand more. Size doesn't change. So this is thought. See, this is something which gained popularity when they claim that carbon nanotube will have a strength more than steel. Just think over it. If you just reinforce it using steel, if you can put steel in this tube, how strong it will be. So this is why the nanotechnology or nano materials became popular. And the characterizations of the nanomaterial. How I would know that this is nanomaterial or this is not nanomaterial? The typical techniques which are used, which I have used, they are called scanning electron microscope, transmission electron microscope, X-ray diffraction, and atomic force microscope. The first three I have used very widely, very frequently used them in my PhD work. And some of it I am going to show you in the next slides. What is XRD? You must have studied in the first year of physics, X-ray diffraction. The Bragg's law and the Shearer's formula. So this is a typical XRD pattern of silicon nanoparticles I am showing you here. This is the bulk material you can see here. This is the nanomaterial. Pure silicon, and then this was after ball milling. I'll try to understand this. Although this is nano, but the crystallinity is lost. The properties do change, I told you. Here you can see the sharp peaks. Very sharp peaks are seen here. Because the material is crystalline. Material is crystalline, sharp peaks indicate the crystalline material. At 28 degrees it confirms that it is silicon. So at 2 theta 28 degree, that indicates it is a silicon peak. The material is silicon. Now after 30 hours of ball milling, now in my laboratory what I did is that I wanted to convert it into nanomaterial, silicon nanoparticles. I took this bulk silicon and milled it for 30 hours. 30 hours of milling in a ball mill, mechanical milling. And then it further reduced, the particle size further reduced. But what happens when you break a crystal, the crystallinity is lost. The fine crystals are not remaining there, now the material becomes a more amorphous kind of material. There are irregularities in the material. And you can see the peaks have got disturbed now. Now there are no sharp peaks, but there are peaks, so it is not complete. The material, the basic material is crystalline, but it has not lost all its crystallinity, but it is reduced. The same thing happens when the nanomaterial or any material have a reaction with any other material. So now just try to understand this. This above images of the pure material, it is similar images and they are almost same. Only difference is that the peaks are labeled. There is 111 plane, there is 320 plane, there is 311, 400, 331. These are the lattice planes that are labeled here on the X-ray diffraction map. And then I did work on the hydrogenation of materials and dehydrogenation of materials. But I wanted to understand how much hydrogen silicon can react with. I did some experiments in my laboratory there at IIT Bombay during my PhD. I exposed these silicon nanoparticles to hydrogen, pure hydrogen gas. And then what happens? The material will change. It becomes SiH. It starts forming silicon hydrogen bonds. If it's a chemical reaction, it will simply absorb hydrogen on its surface irregularities or surface phenomena. Adsorption, that is called adsorption, not absorption. So, but what happens to the crystallinity? Again, you can see the crystallinity is reduced. So, you can see some sharp peaks at the major peaks. but then it is not perfectly crystalline now. At 2 theta angle 27, you still see a 27, 20, you still see a sharp peak indicating that it is hydrogen. It is silicon with hydrogen. Then there is you might be knowing this, the Scherer's formula. Beta 2 theta is equal to k lambda upon L cos theta. This is beta. B is full width half maximum at the most significant peak. When you take full width half maximum, then you can use this to find out the distance between the two lattice planes. This is the significance of this is how the diffraction takes place. An X-ray radiation incident on the plane, it hits the atom here and it gets diffracted. Another X-ray hits another atom in the corresponding or sequential plane and it again diffracts here. The angle of diffraction is theta. And then this, because of the constructive interference, you see a very sharp peak at this. In that case, this is crystalline. There will be another coming from here also again. And then d is the distance between the two planes. This is what you can calculate using Scherer's formula. Or you can validate it using a TM structure. I'll show you in the next slide. These are the transmission electron micrographs of silicon nanoparticles and carbon nanotubes. So now these CNTs were synthesized by my lab mate in IIT Bombay. And this is a picture of a silicon nanostructures, nanoparticles. You can see this is a, you can see the scale is 2 nanometers. So in these 2 nanometers, if you see properly, you will be able to see that there are some lines. You can see the inclined lines. They are atomic planes actually. And I validated it with the XRD, the difference that D I calculated from the Scherer's formula, the distance I measured from here. This is very nothing. Matches quite closely. So this is how you find out whether the butter is nano or not. Now this is 2 nanometers. If you see the distance between the two planes, it would be something around 0.1 less than that. And this dots, what you see, they are the atoms, actual atoms. You can see the TM of the silicon nanoparticle. These are carbon nanotubes, single wall CM. The whole total scale is 20 nanometers and this insert is 2 nanometers. You can see this encircled part here. Then moving to the applications part, let's discuss this. What are the applications of nanotechnology as such? It can be used in the information technology for faster and more energy efficient and powerful computing and other IT-based systems. Miniaturized sizes. In energy, you find most applications in energy. Most efficient and cost-effective technologies for energy production, solar cells, fuel cells, batteries, biofuels, etc. Okay, I can say it today, but I don't know whether it is really cost-effective or not. But yeah, it would be when you do that at a larger scale. In the medicine, typically the nanotechnology applications are more seen in the medicine field, more in the medicine and energy, not in other fields. Only in medicine and energy. Like you can think of cancer treatment, bone treatment, drug delivery, appetite control, drug development, medical tools, diagnostic tests and imaging. A lot of applications in medical. And they talk about consumer goods like the foods and beverages, advanced packaging materials. Then the sensors and lab on chips for food quality testing. In textiles, the waterproof clothing and wrinkle-free textiles, household and cosmetics. A lot of applications are there. And you can see these these videos you will be able to see. You just search for this. And the robots will work in medicines, how they will work. You will see these videos in YouTube. They are all there on the YouTube. All the robots, the nano robots. What the scientists feel is that injection is a very common thing. Now, if one can inject the nano robots in the bloodstream, these nano robots can travel through the blood, go to your arteries where there is a blockages, clean up the blockages, and go out through the urine passage. That's what people talk about. But then, how effective, or how practical it's going to be, nobody knows today. We are working on the structures. Just creating a structure, a working structure at this scale is a most complicated and the complicated thing. Well, there are tiny tools you can see. The nano robot is nano robot, so the tools will be even smaller than that. Clean up your teeth or clean up the things. So there are small nano machines, very small nano machines, but then they're very complicated to make. Like I told you, the arteries can be cleaned up by them. Because it's working in the bloodstream full, nibble out at the arteriosclerotic deposits, widening the blood passages. Now, what is done today? Today they put a stent there and they try to increase. In between here, they put some small tube kind of a thing that will increase the size. It increases and allow the blood to flow. We call it angioplasty nowadays. But then the nanobots can actually go inside the bloodstream and clear the blockages. That is what the scientists think. That is the future. They can take away fight the bacteria to support the immune system. There can be provided some sensors which will lead to identifying the bacteria or identifying the cells which are not the body friendly cells also, and can be killed by the nanorobots. Similarly, the same thing can be done with the cancer cells also. That may lead to advanced cancer treatments. It will be very costly, but then they will be sure shot treatment. It will be controlled by computer, controlled by the artificial intelligence nowadays. A lot of things are, and they're all linked together. Like, see, making nano materials is not a job of a man. It can be done, cannot be done with your hands. You cannot go to your workshop and make a nano robot. You will have to sit inside a lab and do it. Rather, you will not be able to do it. You will have to apply some machines, artificial intelligent machines or robots to make that. Because you cannot work at that small scale. You cannot even see that. Nanomaterials cannot even be seen at that scale. That is the last slide here. I'm going to stop here now. Maybe some other lecture I'll discuss in details about these individual categories. Okay, thank you all for patient listening. Thank you.
Thank you very much, sir, for giving this valuable informative session. Now, I would like to request Dr. Mulla to take a charge and give vote of thanks. Thank you.
Thank you, madam, and thank you, sir, for having very nice session about nanotechnology and nanomaterial. I would like to request all participants, if you have any questions or any doubt regarding nanotechnology and nanomaterial, please ask the question. If you have any question or doubt, you may ask freely, or you may pass the question through message box. Okay, there is no question from audience. I hope you understood the concept of nanotechnology and nanomaterial. So I thank all